So section 2.2 is characteristics of quadratic functions, and we're going to focus mostly on like graphing quadratics that are in different forms. So we've talked a little bit about vertex form, we've graphed quadratics using the parent function transformations, but now we're just going to learn a couple of different ways that we can do this. So it says axis of symmetry is a line that divides a parabola into mirror images and passes through the vertex. So in the last lesson, I mentioned the axis of symmetry, but it's just a vertical line that goes through the vertex, and a parabola is symmetric, just like absolute value. And so you can use that axis of symmetry to find points on one side of it and then reflect them over to avoid having to find more points. So because the vertex of f of x equals a times x minus h squared plus k is hk, talked about this last lesson, the axis of symmetry is the vertical line x equals h. And there's going to seem like there's a lot of things in this lesson that you have to memorize, but it's not really critical to memorize anything because you can get through it with logic and reasoning, and I would much rather you do that. But these are just kind of like helpful tips to get us started. So in addition to graphing quadratic functions in vertex form using transformations like we did in the previous lesson, you can also use the axis of symmetry and the vertex to graph quadratic functions written in vertex form. So for example 1 and example 2, both of these are in vertex form, and I'm just going to rewrite this up here so we have it in front of us. And we're going to graph it in vertex form, but we are no longer just going to focus solely on transformations. We're going to just use the knowledge of where the vertex is and our axis of symmetry in order to find some points. So it's a times x minus h squared plus k. That's our vertex form, and we just have to be able to pull out what h and k are really in order to get started. So if we figure out what our AH and K values are, the A value really doesn't matter that much, but we'll just pull it out just for the sake of identifying it. So A is, if we look at example 1, graph f of x equals -2 times x plus 3 squared plus 4. It says label the vertex and axis of symmetry. So A is always kind of like that coefficient on front, so A is -2. H is being taken away from the x value, so since we have an x plus 3 in here and there's normally a negative, that actually means there's a double negative in here. So h is -3. And then I have plus 4 after, so my k is +4. So once you have h and k, you can go ahead and graph the vertex. So the vertex is, again, the vertex is h comma k, so it's -3, 4. So I can plot that point. So -3 and then up 1, 2, 3, 4. That's my vertex. And then the axis of symmetry is a vertical line that goes through the vertex. So on the last page, we talked about the axis of symmetry is the line x equals h. That's just because it goes through the vertex. So it said x equals h, or oops. Talked about it being x equals h, so that just means it's like any vertical line is x equals. This just happens to be whatever the h value is since it goes through the vertex. So our axis of symmetry is x equals -3, so that's our h value. And then from there, we can just evaluate the function at a couple of different x values in order to find our points. So you can set up a table if you really want. You don't have to. If you really wanted to use transformations, you could, but it'd probably take a little bit longer the more transformations there are in the function. So what we're going to do is we're going to just find 2 other points and reflect them to get our remaining 2 points. We want 5 points total. So how I want you to decide what x values you need to plug into your function is you're going to pick 2 that are either directly left or directly right from the vertex. So I can either pick, so the vertex is at -3, 4. I can either pick x equals -2 and x equals -1, or I can pick x equals -4 and x equals -5. So just make sure they're both on the same side, both right side or both left side, and then you can evaluate them. So I'm going to use x equals 2 and x equals negative 1. I'm going to go on the right side. So I'm going to evaluate the function at x equals negative 2. So that'll be f of negative 2 equals. I'm just going to plug in x equals negative 2 into this function. So negative 2 times negative 2 again, plus 3 squared plus 4. From there, I'll simplify it. So negative 2 times negative 2 plus 3 in the parentheses, that's 1 squared plus 4. Negative 2 times 1 squared is just 1. So that becomes, that stays as negative 2 plus 4. And then negative 2 plus 4 is positive 2. So when I substituted in x equals negative 2, I got a 2 out. So that is a point. So that tells me I have a point at negative 2, positive 2. The value I plug into the function is my x, or my input, or my domain. The value I get out is my output, or my y value. So I have a point at negative 2, 2. So I'm going to go ahead and I'm going to plot that point now. So negative 2, 2. And then from there, because parabolas are symmetric, I can take this point and I can reflect it over the axis of symmetry. So it goes from, and when I reflect it, the height is not going to change. I'm just literally just bouncing it over. So it goes from 1 to the right of the axis of symmetry to 1 to the left. Distance doesn't change, the height doesn't change, just the side that it's on changes. And then so now I have a point 1 away from the vertex on both sides, and I need to go 2 away. So I'm going to go, and again, it doesn't matter which side as long as you are going a further distance away. Like you wouldn't want to plug in x equals negative 4 now because we just found that point. So I'm going to substitute in x equals negative 1 because that would be 1 unit further away from the vertex. So I'm going to evaluate f of negative 1. I'm going to plug x equals negative 1 into my function. So negative 2 times negative 1 plus 3 squared plus 4. Negative 2 times negative 1 plus 3 is 2 squared plus 4. Negative 2, I'm going to square my 2 first. Just order of operations, exponents before multiplication. So negative 2 squared is 4 plus 4. And then I have to go left to right now, I'm sorry. So negative 2 times 4 is negative 8. And then plus 4. Negative 8 plus 4 is negative 4. So when I plugged in negative 1, I got negative 4 out. So that means I have a point at negative 1, 4. This is my input, my x, my output, my y. So negative 1, negative 4. I found my 2 points from just evaluating the function, and those 2 points will each give me an extra point, so I'll have 5 altogether. So I just found the point negative 1, negative 4. So I'll go left 1 down 4. And then now I need to take that point and I need to reflect it to get my last point. So again, the height of the point won't change. The distance from the axis of symmetry won't change, it just flips over. So it goes from 2 to the right to 2 to the left. And then now I have 1, 2, 3, 4, 5 points. So that's all you need for quadratics and absolute value for that matter. Now you can go ahead and connect your points. And I just want to reiterate again, because this is one of the harder parts about this to remember. When you're picking the numbers to substitute in here, you just go 1, 2 away from the vertex. So my vertex was at x equals negative 3. So I went to x equals negative 1, 1 to the right, and then I went to, I went to x equals negative 2, 1 to the right, and then I went to x equals negative 1, which is 2 to the right. So I went 1 and 2 over. Most problems are going to be exactly like that as far as how far away from the vertex you need to go. There may be a couple of problems here and there where maybe you want to go a little bit further away. So for example 2, it's f of x equals 2 times x minus 2 squared plus 5. So you can kind of pick out what your a, h, and k are. So a is a coefficient, a is 2. And then for h, Remember, h is what's being taken away from x, so my h value is 2. Remember, you already have the negative embedded in there, so this means h is positive 2, and then my k value is 5. So we know that the vertex is h comma k, so my vertex in this case is going to be 2 comma 5. And you can go ahead and graph that right away. So 2, 5 will go right to up 5, and that'll be my vertex. I'm not going to write it there because I feel like it'll get messy. But now that I have my vertex, I also know my axis of symmetry, so it's just a vertical line that goes through my vertex. And any vertical line is in the form x equals, like x equals just a number. And since it goes through the vertex, that number is going to be the same as the h value because that's the x-coordinate of the vertex. So my axis of symmetry is x equals h, so it's x equals 2. This line is x equals 2. So now that I have all that set up, now is when I can start evaluating the function for a couple of points in order to find like the rest of the points I need to fill in the graph. So again, you can either go like 1 and 2 to the right or 1 and 2 to the left. It's totally like up to you. It does not make a difference. I'm gonna go just 1 and 2 to the left this time when I pick my x values. So if my vertex was at x equals 2, 1 to the left of that, or 1 to the left of the axis of symmetry in general, is going to be x equals 1. 1. So I'm going to evaluate my function at f of 1. So that's my first input value that I'm going to use, and that's going to just take me 1 to the left. So f of 1, I just have to plug in 1 for x. So 2 times 1 instead of x minus 2 squared plus 5, and then 2 times 1 minus 2 would be negative 1 squared plus 5. I'm going to square the negative 1 before multiplying by the 2. So negative 1 squared is positive 1 plus 5. And then 2 times 1 is just 2 plus 5, so 7. So now I have the point when I substituted in x equals 1, I got a 7 out. So my input was 1, my output was 7. So I have the point 1, 7 on my graph. And I can go ahead and plot that right away. So 1, 7, I'll go right 1, up 7. And then I went 1 to the left of the axis of symmetry, so now I'm going to go 2 to the left. So don't like go 1 left and 1 right, because the one to the right is just a reflection, and I can go ahead and reflect it now. It's symmetric, so the height is not going to change. I'm just going to go from 1 to the left of the axis of symmetry to 1 to the right. So that point ends up being at 3, 7. So now I went 1 away, so now I'm going to go 2 away, and I'm just going to go to the left. That'll be at x equals 0. So I need to evaluate the function at f of 0. So I'm just going to use that same function and substitute in 0 for x. So 2 times x, or sorry, 0 minus 2, once I substitute in that 0, squared plus 5, and then simplify from there. So in the parentheses, I have 0 minus 2, so negative 2 squared plus 5. I'm going to square before I multiply, so negative 2 squared is positive 4 plus 5. And then 2 times 4 would be 8 plus 5 equals 13. So when I substitute in 0, I got 13 out. My input was 0, my output was 13, so I have the point 0, 13 on this graph, and it may not fit, and that's okay. One thing though, I know that the 0, 13 doesn't fit on my graph. I don't necessarily expect you to draw like a huge graph, but I do expect you to show the math for it. So even if you're not plotting this point, you're showing yourself getting this second point here, or really this third point here. So again, I'm not going to graph it, but I want to see the math. From there, you can just connect to these 3 points. Just remember, it's going to be fairly narrow because it's a little stretched. So if we connect those points, remember, it's like a nice U shape, not a V shape. And yeah, now you have a good graph. just for the most part, if you're capable, try to fit it on your graph, and if not, just do your best to draw an accurate graph. So quadratic functions can also be written in standard form, and standard form may look pretty familiar. It's f of x equals ax squared plus bx plus c, where a can't be 0 because then the x squared disappears. So standard form can be derived by expanding vertex form, and expanding vertex form just means, I'm going to go up to vertex form really quick. Expanding vertex form just means like foiling this out and then simplifying it until it's in standard form. So a in standard form, so the coefficient of x squared, has the same meaning as in vertex form, so it still means like there's a stretch. And then the axis of symmetry is x equals negative b over 2a, and c is the y-intercept. So this is where, to me, it feels a little bit like memorizing, like when you first look at the notes, but it doesn't have to be. A lot of it is very just like logical, or like if you look at a graph, you can figure out certain points from the graph. One thing, the reason that c is the y-intercept is because we talked about the y-intercept is anywhere where x equals 0. Like on a graph, if x equals 0, whatever point is at x equals 0, that'll be your y-intercept. And if I were to evaluate this function or any standard form function at x equals 0, this would cancel out and this would cancel out, and you'd just be left with c. So that's why c gives you the y-intercept. So properties of the graph of standard form quadratic. This graphic can be found in your textbook if you want to look at it more closely later. But for when a is greater than 0, that means that the graph opens up and you have a minimum. So, and then when a is less than 0, or the coefficient of a squared is negative, the graph opens down and you have a minimum. Either way, your axis of symmetry is going to be x equals negative b over 2a. That's just that vertical line that goes through the vertex. So the graph is narrower than the graph is narrower than the graph of just the parent function f of x equals x squared when the absolute value of a is greater than 1, meaning there's a stretch if the absolute value of a is greater than 1, and wider when it's less than 1. That's just talking about stretch and shrink. And then we just talked about axis of symmetry is x equals negative b over 2a. This at first sight may look a little bit confusing. It's just the vertex is this negative b over 2a and f of negative b over 2a, because if we can find this axis of symmetry, so say I find this line, if I want to figure out at what point this line crosses through the function, I just have to evaluate it at that function. I hope that makes a little bit more sense once we start getting to the problems. And then we just talked about why the y-intercept is c. So for the graph of f of x equals 3x squared minus 6x plus 1, and it says label the vertex and the axis of symmetry. So there's a few different pieces that we need to find. We can identify what a, b, and c are at first. Some of them will be more helpful than others, but we'll start with that. So a is equal to 3, and again, I'm going to rewrite the standard form up above. So f of x equals ax squared plus bx plus c. So a is 3, b is negative 6, and c is 1. So knowing that c gives you the y-intercept is just kind of like a helpful shortcut. It's not essential that you remember that, but it does help you. So if c is 1 and we know that c is the y-intercept, that means that the point 0, 1 is on the graph, because that would be our y-intercept. And then the main thing that you have to remember for standard form is the axis of symmetry and what that little, I guess, like mini formula is. So the axis of symmetry is x equals negative b over 2a. So if we pull out a and b and we substitute them in here, negative b would be negative negative 6. And then over 2 times a, so over 2 times 3. So negative negative 6 is positive 6 over 2 times 3, so over 6, so that is 1. And then I'm just going to start by graphing the axis of symmetry. So again, that was x equals 1, and that's just a vertical line through x equals 1. And then from there, if we want to figure out what the vertex is, I'm going to write it in that kind of, I guess, like function form for lack of better terms. So the vertex is negative b over 2a and then f of negative b over 2a. So what that means is I know that if this is the axis of symmetry, that the vertex is going to be somewhere on this line. I just don't know where. So if I want to figure out where this line, I guess like intersects for lack of better terms, with the quadratic or with the parabola in general, I need to evaluate the function at f of 1 because I want to see where it crosses here. So if we figured out what negative b over 2a was, and that was 1, that just means that next we need to find f of 1. So you're finding f of whatever you got for the axis of symmetry. So f of whatever negative b over 2a is. So if I want to find f of 1, and that'll give me my vertex, f of 1 is, so 3x squared becomes 3 times 1 squared minus 6 times 1 plus 1. And then 3 times 1 squared is just 1, so that's 3 minus 6 times 1, so minus 6 plus 1. 3 minus 6 is negative 3, plus 1 is negative 2. So when we found f of 1, we got negative 2 out. So that means that the vertex is the point 1, negative 2. And that's my negative b over 2a and f of negative b over 2a. It's the axis of symmetry, and then where that axis of symmetry intersects with the parabola. So I'm going to plot that, and then we'll go forward from there. So the vertex is at 1, negative 2. And then we talked about how the y-intercept is 0, 1. So we know 0, 1 is on the graph. So I'm just going to have that be my first point. So 0, 1. And then that's like a nice point that's 1 unit away from the axis of symmetry. I can go ahead and reflect that point too. So it goes from 1 to the left of the axis of symmetry to 1 to the right. And if you're able to graph the y-intercept, you should graph that before finding another point. Because initially, like, I probably would have just wanted to go either 1 to the left or 1 to the right of the axis of symmetry. And I just would have ended up with the point that I already have. So I would graph that first, and then you figure out where you can go from there. So since I already have the points that are 1 away, I need to now go 2 away. So I can pick x equals negative 1, or I could pick x equals 3. So I'm going to pick x equals 3. Again, it really doesn't matter. It's whatever you want to work with. But because we already have the points that are 1 away from the axis of symmetry, we need to go 2 away. So 2 away would be x equals 3, so that's what I'm going to do. So I'm going to evaluate f of 3. So I just need to take x equals 3 and substitute into the function. So that'd be 3 times 3 squared minus 6 times 3 plus 1. And then I need to square before I multiply. So 3 squared is 9, so this becomes 3 times 9. Minus 6 times 3, so minus 18 plus 1. And then that's 3 times 9, so 27, minus 18 plus 1. And then 27 minus 18 is 9, plus 1 would be 10. So when I substituted in 3, or when my input was 3, my output was 10. So the point 3, 10 was on the graph. So now I can graph that 3, 10. So write 3 up 10, and then I can take that point and I can reflect it over the axis of symmetry. So it goes from 2 to the right to 2 to the left, so over at negative 110. And if you had picked like x equals -1 to evaluate the function at originally, you would have ended up with 10, 2, and just been able to reflect it. And then from there, you can just go ahead and connect your points. So try as much as you can to get 5 points on there. If the points get a little too stretched or a little bit too shifted off the graph, that's okay. Just as long as you're showing all of this work, that's what's really most important. So example 4 is graph f of x equals -2x squared minus 8x plus 1. And we want to label the vertex and the axis of symmetry. So this is in standard form, so I'm just going to start by kind of pulling out my a, b, and c. So again, a is the coefficient of x squared, so a is -2, and then b is the coefficient of x, so b is -8, and then c is the constant, so c equals 1, and c also tells us our y-intercept. So since c equals 1, that means that our y-intercept is 0, 1, so one of our points is 0, 1, so that's on our graph. And then the next thing that we need to do is need to find our axis of symmetry. So axis of symmetry is the line x equals -b over 2a. So -b, negative, and then b is -8, so -8. And then over 2 times a, so 2 times -2. -8 turns into +8 over 2 times -2, which is -4. And then 8 divided by -4 turns into -2. So we found the axis of symmetry. You can start by graphing that if you want, if it helps you visualize it more. So x equals -2, just a vertical line. Through x equals -2. And since we found that the axis of symmetry is x equals -2, that means that the vertex will be the point -2 and then f of -2. So whatever we evaluate the function at -2. So we have to find this f of -2. It's not just given to us, we have to find it. So f of -2 is going to be the function evaluated at x equals -2. So -2 times x squared, so times -2 squared, minus 8 times -2 plus 1. And then I'm going to square my -2 first. So -2 times -2 squared would be +4. And then -8 times -2 would turn into +16 plus 1. -2 times 4 is -8 plus 16 plus 1. -8 plus 16 is 8 plus 1 would be 9. So that means that my vertex is -2, 9. My vertex is -2, 9, so I can go ahead and plot that point. So -2 and then up 9. And then we also know that our y-intercept is 0, 1. So we can plot 0, 1 right off the bat. And I can also reflect that over the axis of symmetry. So 0, 1 goes from 2 to the right of the axis of symmetry to 2 to the left, so it goes over to -4, 1. And then I have 3 points, so I just need one more point in order to reflect it and then get my 5th. So I have points that are 2 away from the axis of symmetry, so now I just want to go 1 away. I kind of want to backtrack. So you can either pick x equals -1 or x equals -3. It's up to you. I'm going to use x equals -1. So I'm going to evaluate the function at x equals -1. So it would be -2x squared. So -2 times -1 squared minus 8 times -1 plus 1. And then I'm going to square the -1 first. So -2 times +1. -8 times -1 is +8 plus 1. -2 times 1 is -2 plus 8 plus 1. And then -2 plus 8 is 6 plus 1 is 7. So when I input -1, I got 7 out. So the point -1, 7 is also on the graph. So -1, -7, I'll go left 1, up 7. And then that point is 1 to the right of the axis of symmetry, so I can reflect it over to 1 to the left. So 1 to the right, over to 1 to the left, and then I can go ahead and connect those points. And then the next section we're going to talk about is finding maximum and minimum values. So because our vertex is HK when it's in vertex form, that's the highest or the lowest point in the parabola. It's y coordinate, so like the height of that point tells you a minimum or maximum value of the function. And this is something that like comes like really in handy into like application problems. So the vertex lies on the axis of symmetry. So if the function is increasing on one side of the axis of symmetry or the function is increasing on one side of the axis of symmetry and decreasing on the other. Again, that type of information is just something that's like very, very helpful for when we get to any sort of like modeling or application problem. So this graphic didn't really print that well, but again, in your textbook in 2.2, so you can kind of look it up if you want to see it a little bit better. So when we're looking at standard form, it says for the quadratic f of x equals ax squared plus bx plus c, the y coordinate of the vertex is the minimum value of the function when a is greater than 0, and the maximum value when a is less than 0. So basically, like when a is greater than 0, the function opens upward, so we have a minimum value. The y coordinate of the vertex is a minimum. And when a is less than 0, the graph is opening downward, so the vertex or the y coordinate of the vertex is a maximum or a high point. Maximum minimum is just talking about high, low point of the function. So I'm not going to get a whole lot into this or into it in detail, because I think if you want to look through it, it's in the textbook. But we're just going to kind of try to think logistically like through the function itself in order to evaluate those. So it says find the minimum or the maximum value of f of x equals 1/2 x squared minus 2x minus 1, and describe the domain and range of the function and where the function is increasing and decreasing. So we have to find a lot of different parts for this, and that's okay. We'll just kind of work through it piece by piece. So this is in standard form. So we have ax squared plus bx plus c. So I'm just going to first pull out a, b, and c. So a is 1/2. B is the coefficient of x, so -2, and c is the constant, so -1. So the first thing that we're going to do, really the first thing you do like when you're dealing with quadratics, graphs of quadratics and stuff like that when it's in standard form, is we need to find the axis of symmetry, because even if we're not graphing it, it tells us so much about the function itself. So remember, the axis of symmetry is x equals -b over 2a. So x equals -b over 2a, so I just have to substitute those values in. So -b be -2 over a, so over 1/2. And then -2 turns into +2. Oops, I forgot the 2 times. The 2a, sorry. So -b is -2, and then over 2 times a, so over 2 times 1/2, which makes it a little bit easier. So -2 turns into +2, and then 2 times 1/2 is just 1. So my axis of symmetry is just 2. X equals 2. So I'm just going to kind of like draw a little sketch of a quadratic to help us like picture what this is going to look like. So our A is positive. So our A is positive. That means that the graph is going to open upward, and our vertex is going to give us a minimum. Okay, so our vertex gives us a minimum. That means if we can find the vertex, or we can actually find the value of like the y-coordinate of the vertex, that tells us our low point. So we just found the axis of symmetry, and when we were graphing, what we had to do after we found the axis of symmetry, we had to take that value and evaluate the function there. So we need to find f of 2. F of 2 is going to give us a minimum. It's going to tell us the y-coordinate of the vertex. This is just the x-coordinate of the vertex. So f of 2 will tell us the minimum. So I'm going to evaluate f of 2. Our function was 1/2 x squared, so 1/2 times 2 squared, so I'm substituting in 2 for x. And then minus 2 times 2 minus 1. And then I'm going to square the 2 first, so 1/2 times 2 squared is 4, minus 2 times 2, so minus 4 minus 1. And then 1/2 times 4 is 2, minus 4 minus 1, so 2 times 4 is negative 2, minus 1 is negative 3. So that negative 3 is a minimum. If you're picturing this graph in your head, we found the vertex pretty much, because we found the axis of symmetry and then substitute that in to get the height of the vertex or the y-coordinate. So if you're picturing the graph in your head, the vertex would be 2, negative 3. So we're not doing really any different math, we're just applying it in a different way. So we found the minimum. It says next to describe the domain and the range of the function. So our domain for any quadratic, just like any absolute value, is all real numbers, because there's really no limitation as far as what input value I can use and get a real value out. So our domain is all real numbers, but the range does have a restriction. And it talks about that graphic up here, kind of what the range is, but I just would rather you kind of think about it like reasonably with the graph. So we found out that there's a minimum of negative 3. So that just means the lowest possible point on the graph is negative 3. So our range has to be either, it could be equal to negative 3 or it can be greater than negative 3. So our range is going to be y is greater than or equal to negative 3. The range depends on the minimum. The minimum is exactly what it sounds like, it's just the lowest possible point. And then it says evaluate where the function is increasing or decreasing. So I would try to, kind of like how I drew this little graph, that'll really help you picture where it's increasing or decreasing. When we're talking about increasing or decreasing, we're looking from left to right. So if we look at, like, for example, this one, because this graph also opens up, if we look at the graph from left to right, the graph is going down to the minimum, and then once it hits the minimum, it increases. So it's basically going down to the vertex, and the vertex is this x value, or this coordinate right here, is something that we already found in the form of the axis of symmetry. So that's what the increasing or decreasing is going to be bounded by, is whatever the axis of symmetry is. So we found out the axis of symmetry was x equals 2. We found that up there. So if we want to figure out where the graph is decreasing, the graph is decreasing before we get to the axis of symmetry. So the graph is opening up, so from like left to right, it's going towards the axis of symmetry or towards the vertex, and it's going downward. So it's decreasing to the left of x equals 2, because that was our axis of symmetry. So it's decreasing to the left of x equals 2, and then once it hits x equals 2, once it gets to that minimum or the vertex, sorry, not the minimum, but the vertex or the axis of symmetry, then it starts increasing. So it's increasing to the right of x equals 2. So for example 6, it says find the minimum or the maximum value of f of x equals 4x squared plus 16x minus 3. Describe the domain and range of the function and where the function is increasing or decreasing. So similar to the last problem, It's in standard form, so first I'm just going to pull out a, b, and c. A is the coefficient of x squared, so a is 4. B is the coefficient of 16, or sorry, the coefficient of x, so b is 16. C is the constant, so c is -3. So the first thing that we need to do in order to find the minimum, find the vertex, kind of all the same idea, is to figure out what the axis of symmetry is, because that'll tell us a lot about this function. So the axis of symmetry is x equals -b over 2a. So -b would become -16 over 2 times 4, -16 over 2 times 4, so over 8, and then -16 divided by 8 is -2. So if we think about what this graph is going to look like, it's a is positive, so this graph is also going to open upward. And that's important to think about to decide whether you're getting a minimum or a maximum out of this function. So each parabola will have either a minimum or a maximum, not both. So a is positive, so that means the graph opens upward and we have a minimum at the vertex. So we just found the x-coordinate of the vertex. So we need to find the y-coordinate, or like kind of like the height of the vertex, in order to figure out what the minimum actually is. So we just need to evaluate the function at x equals -2. So f of -2 will be our minimum. So I'm going to evaluate the function at f of -2. So f of -2, I just have to substitute that x equals -2 into the function where x is. So 4 times -2 squared plus 16 times -2 minus 3. And then square the -2 first. So -2 squared is +4. So 4 times 4. 16 times -2 would be -32 minus 3. Sorry, I have to go left to right now. So 4 times 4 is 16. Minus 32 minus 3. 16 minus 32 is -16. Minus 3 is -19. So -19 is our minimum. And thinking about what that looks like on the graph, that just means that if we were to graph this, we would have a vertex, or the vertex would be at -2, -19. So -19 is our minimum, and once we find the minimum and the maximum, we need to figure out domain and range and whether or where the function is increasing and decreasing. So if we want to figure out domain, we need to think about what are all the possible x values or input values that I can use and get a real number out. For any quadratic function, it is all real numbers. And then for range, we just found out that the minimum value was -19. So that's what the range is dependent on. If I'm saying there's a minimum, I'm saying there's no possible lower value than -19. So it could be equal to -19, or it could be greater than -19. So the range is going to be y is greater than or equal to -19. And then to figure out where it's increasing or decreasing, that's where it's also very helpful to just like draw yourself a little sketch of it opening up if a is positive, or opening down if a is negative. So where it's increasing or decreasing is also going to be dependent on where the vertex is or where the axis of symmetry is. Because this point where it like changes direction, changes from decreasing to increasing, this is the axis of symmetry. So that in this case is x equals -2. So because it opens up, it starts off decreasing. It's decreasing to the left of the axis of symmetry. So in this case, it's decreasing to the left of x equals -2 because that was the axis of symmetry that we found. And then once it hits that axis of symmetry, once it hits a vertex, it starts increasing. It starts going up from left to right. So it's increasing to the right of x equals -2. And then last one of these, so like if you're ready to try one on your own, I would pause it and then maybe use it to check your answer. But B is find the minimum or maximum value of h of x equals -x squared plus 5x plus 9. So my phone ran out of storage during the last example, and I didn't notice that the video stopped, so I did it all by my lonesome. But I'll just kind of talk through this, and then I will do this example in class over like live Zoom time. So it says find the minimum or maximum value of h of x equals negative x squared plus 5x plus 9. Describe the domain and range of the function and where the function is increasing or decreasing. So it's standard form, so we pulled out a, b, and c first. So like a was the coefficient of x squared, so that's negative 1. B is 5, that's coefficient of x, and then the constant is 9. So the first thing that we have to do is we have to find the axis of symmetry. So that is a equals negative b over 2a, or sorry, x equals negative b over 2a. B was 5, so this is negative 5 over 2 times 1, so over 2 times negative 1, or 2 times a, sorry, so 2 times negative 1. And then negative 5 over 2 times negative 1 is negative 2, so negative 5 over negative 2, and a negative 5 by negative is a positive, so just end up with x equals 5 halves. And then next we have to kind of decide is it going to be a max or a min. So because a is negative, that means that the graph opens downward. So instead of having a minimum like in the other two problems, we have a maximum just because a is negative. So finding f of 5 halves, that will tell us our maximum this time. So f of 5 halves, when we substitute the 5 halves in, it's negative 5 halves squared plus 5 times 5 halves plus 9. And then for the squared part, the negative is not being squared since it's like not in parentheses with the x. So just the 5 halves is being squared there, and then it will make it negative after. So if I square a fraction, it just means I have to square the numerator and square the denominator. So 5 squared would be 25, 2 squared would be 4, so this would turn into negative 25 over 4, plus 25 over 2 plus 9, and then I wanted to get common denominators here to be able to add these fractions. So I multiplied 25 over 2 by 2 over 2. So this negative 25 over 4 I left the same. 25 times 2 was 50, 2 times 2 got me over 4. Plus 9, and then negative 25 fourths plus 50 fourths was positive 25 fourths plus 9, and then from here I just changed it to a decimal. So 25 over 4 is 6.25 plus 9 was 15.25. So all that gave us our maximum, and then from there we can describe domain and range, and then where it's increasing and decreasing. Domain hasn't changed, it's still all real numbers for any quadratic function. For the range, 15.25 is my maximum value. It's the highest that function will ever possibly be. So for the range, like y can be equal to that maximum or it can be less than. So y is less than or equal to 15.25. And then for where it's increasing or decreasing, since the graph is flipped upside down, this is a little bit different. So I know my axis of symmetry is a vertical line that goes to the vertex, and we found that axis of symmetry was x equals 5 halves. So in order to figure out where it's increasing or decreasing, it's going to be bounded by like that line x equals 5 halves. So because the graph is flipped upside down, if we look from left to right, the graph is increasing. It goes like up towards the vertex. So it's going to be increasing to the left of 5 halves, and then it's going to be decreasing to the right of 5 halves. But again, I'll kind of do this problem, or I'll redo this problem in class. So the next way that we can graph quadratics is with using x-intercepts. So this typically only falls when it's in a certain form. I guess if it's not in this form and it's a special type of problem, you can factor it into this form. But what we're looking for is when a graph of a quadratic function has at least one x-intercept, the function can be written in intercept form. So intercept form is f of x equals a times x minus p times x minus q, where a can't be 0. So p and q are your intercepts. So because f of p, like if I were to substitute p in for x, is 0, meaning because this would be 0, so everything multiplied by that would become 0. And same thing with f of q, if I were to substitute in whatever the q value is here, this factor would become 0 and the whole function becomes 0. P and q are the x-intercepts of the graph of the function. So the axis of symmetry is always halfway between P and Q since it's symmetric. So the axis of symmetry is going to be x equals P plus Q divided by 2. A lot of the times, like, you could just look at the graph and kind of tell what the axis of symmetry is too, because it's going to be perfectly in the middle of P and Q. And then same thing goes for like our A values. When A is positive or greater than 0, the graph opens up, and then when A is negative or less than 0, the graph opens down. So for example 7, it's the graph f of x equals negative 2 times x plus 3 times x minus 1. Label the x-intercepts, the vertex, and the axis of symmetry. So we can pull out A if we want. A is negative 2, and then just keep in mind that in the formula there's already subtraction signs or negatives here, so it's kind of like vertex form a little bit where you have to flip the sign. So this x plus 3 really means that P is negative 3, and then x minus 1, so that means that Q is 1. And you could switch P and Q, it doesn't really matter. And then we'll go ahead and label the x-intercepts, vertex, and axis of symmetry. So I'm just going to start by graphing the x-intercepts. So I have an x-intercept at negative 3 and at 1. That just means you have points at negative 3, 0, and at 1, 0. So negative 3, 0, 1, 0. And then we know that the axis of symmetry is like perfectly in the middle of those. So like technically you can add P and Q together and divide by 2. So like negative 3 plus 1 is negative 2, divided by 2 is negative 1, so that's our axis of symmetry. But like I said, it's always in the middle too. So perfectly in the middle is at x equals 1. So x equals negative 1. So x equals negative 1, that is our axis of symmetry. And then from there, we can go ahead and find our vertex. So if we know that our axis of symmetry is at x equals 1, we know that our vertex is going to be on that line, but to find exactly where on that line, I need to take that x value and evaluate the function there. So I'm going to find f of negative 1, and then that'll give me basically my y-coordinate of the vertex. So it'd be negative 2 times x plus 3, so negative 1 plus 3 times negative 1 minus 1. So I'll just leave this negative 2 out in front for now. Negative 1 plus 3 is 2, negative 1 minus 1 is negative 2, and then negative 2 times 2 is negative 4, times another negative 2 becomes positive 8. So this was my axis of symmetry, was that x equals negative 1. When that was my input, my output was 8, so that means my vertex is negative 1, 8. So my vertex is at negative 1, 8, so I can go ahead and I can graph that. So left 1, up 8, and then for intercept forms specifically, I'm okay with you just getting the 3 points. So for the other two forms, continue getting 5 points, but for intercept forms specifically, 3 points is okay. So from there, we can just connect our points to finish our graph. And then for example 8, it's graph f of x equals 1/4 times x minus 6 times x minus 2. It says labeled x-intercepts, intercepts, vertex, and axis of symmetry. So I can pull out my a, that's 1/4, that's just that coefficient. And then remember, there's already a negative embedded in intercept form. So it's x minus p, that means that p is 6. And then x minus q, so that means that q is 2. So that means that my x-intercepts are 6 and 2. So I have a point at 6, 0 and at 2, 0. So I can start by graphing those points. So 2, 0, 6, 0, and I know that my y-intercept is, my axis of symmetry is directly in the middle of those. So you can add those numbers together. You can add 6 and 2 and then divide by 2. So 6 plus 2 divided by 2, 6 plus 2 is 8. Divided by 2 is 4, or if you just see that 4 is right in the middle, you can do it that way. It's up to you. So my axis of symmetry is at x equals 4. And then I know that my vertex is going to be somewhere on this line, but to find exactly where it is on the line, I should evaluate the function at x equals 4. Evaluate it just whatever your axis of symmetry is at. So f of 4 is going to be 1/4 times 4 minus 6 times 4 minus 2. And then I'll leave the 1/4 alone for now. 4 minus 6 is -2. 4 minus 2 is +2. And then 1/4 times -2 is -1/2. And then -1/2 times 2 becomes -1. So when I evaluated the function at 4, my input was 4, my output was -1. So my vertex is 4, -1. So I can plot my vertex at 4, -1. And then, like I said with intercept form, I'm okay with you just getting the 3 points. The other two forms, vertex and standard, make sure you keep getting the 5. But for intercept, 3 is okay. And then you'll just connect your points from there. And you can see that this graph has been like stretched out a lot, and it's a lot wider because that a value is 1/4. So that's our vertical shrink. And then for example 9, this is the last one. It says the parabola shows the path of your first golf shot, where x is the horizontal distance in yards and y is the corresponding height in yards. Find the path of your second shot. Can be modeled by the function f of x equals -0.2x times x minus 80. Which shot travels further before hitting the ground, and which one travels higher? So I'm going to kind of rewrite the function that they give us for the second shot. And when this can be, it may not recognize it right away, but this is kind of in intercept form, and I'm going to change the way it's written so that it looks a little bit more like it. So f of x equals -0.02, and then because I just have this x here, that just means that one of the intercepts is 0. So I'm going to write it as x minus 0, just to help us see it, times x minus 80. So now we can kind of easily identify what our two intercepts are. I'm not super worried about the a value for right now, but I do know that p, one of the intercepts, is 0, and q, the other intercept, is 80. And if we look at the graphic that we're given, it kind of helps us make sense of the intercepts. Like the first intercept here, that's the starting point. And then the second intercept, that's where the ball lands. So our first intercept is 0. The second intercept from the equation itself is 80. So that's telling us starting point and landing point. But in order for us to find the high point, or the height, or basically like the maximum, we have to find the vertex, because the vertex tells us our maximum. So in order to find the vertex, we first have to find the axis of symmetry. And remember that the axis of symmetry is just like the halfway point between the two intercepts, or you can use that little formula like the p plus q over 2. So axis of symmetry is x equals p plus q divided by 2. So that was 0 plus 80 divided by 2. 0 plus 80 is just 80, divided by 2 is 40. And again, if you had just like recognized that 40 is the halfway point between 0 and 80, that way is perfectly fine too. But our axis of symmetry is x equals 40. So in order to find the maximum of the function, we have to evaluate the function at x equals 40. So I'm going to find f of 40, and that'll tell me the highest point that the ball has been to. So our function is -0.02 times x, so times 40, times x minus 80, so times 40 minus 80. And then -0.2 times 40, oops, there should be an 8 or a 0 though. Times 40 minus 80, so times -40. And then from there, you can just punch it into the calculator. So negative 0.02 times 40 times our negative 40 should be positive 32. So that, like 40, 32, like this is our input, this is our output. So 40, 32 is our vertex. If you're picturing the graph of this, or if you were like sketching a graph of this, that y value of the vertex is the maximum, or the highest point that the ball went to. So now we have like all the information. We have that the ball from the function itself went a total of 80 yards, and it reached a height of 32 yards. So we can use that information just to compare it to the photo. So I think the photo was shot 1, and then the function itself was shot 2. So just by comparing the information from shot 1 to shot 2, we just talked about shot 2 goes a total of 80 feet, but it went a height of 32 feet. So shot 1 went a total of yards. Shot 1 went a total of 100 yards, but it only went a height of 25 yards. So shot 1 went further by 20 yards, and then shot 2 went higher by 7 yards, because it went 32 yards versus 25 yards.